Good morning, everybody. I think we're nearly in. So I'm going to start right on time because I have far too much content to fit in. So, and we may not have too much time for questions at the end. Don't be afraid to come and find me afterwards and ask me questions if you have any. So yeah, my talk this year is the bits between the bits, how we get to main. And it's one of those sort of topics where, as programmers, we typically don't think about it too much. I mean, certainly, I'm most famous for that website. And that website shows you assembly code, you type in a bit of C and you see a bit of assembly, and you're like, that's cool. But it doesn't really tell you the wider picture, how everything fits together, how the program actually starts up, and how your code actually starts executing. And there's a lot of stuff that goes on before you even get to main. And that's what we're going to be talking about. And some of the tools and behind the scenes, and why some of the things you may have learned along the way about don't do this are so. So first of all, the name, the bits between the bits. How many people have ever heard of the band Ozric Tentacles? Yeah. 1, 2, all Brits. All right, so the bits between the bits was one of their least inspired albums. For some reason, the name stuck with me as being a name for the stuff between the important things that you don't really think about, right? And that's the bits between the bits. Now, I happened to Google for this picture to do these slides, and I found the website Prog Rock or Prog Archive or something, and it described the album as good, but not essential. And I just hope that this is not inauspicious for me. But anyway, we're going to start with a program. This is about the simplest program you could write. Okay, I don't think there are many, short of the white space between the parens and the squiggly bracket things, you couldn't write the smaller program. What does this compile to? I'm going to use GCC, and for the whole of this talk, actually, we're going to be talking about Linux mainly. Just a quick note on that. I don't know much about Windows nowadays, so I'm not really qualified to talk about it. I assume that similar mechanisms to the ones I'm going to be describing happen inside the Windows linker and runtime, but I'm not the right person to talk to you about them. So I'm going to use GCC. This is GCC 8.1, I think, just the one I happen to have on my laptop. And I'm optimizing for size. What is your idea about how this program compiles? How big will this program compile down to? Any kind of thing? So, sorry, what was that? 5 kilobytes. 5K. Anyone higher than 5K? 13. 13K. Any more? 42K. 42 bytes? No, 42K. Yeah, you're all in the right ballpark, right? The C version here, if I compile that as a C function, as a C program, sorry, 7976. Okay. So I think we award a prize over there. How much do you think the C++ program compiles to? 100K. 100K, exactly the same. Turns out if you're not using the features, you don't pay for them. Thematic, I think. I was surprised as well. I mean, the binaries are different. There are some things, there's some padding going on, which means that the slop in one is taken up by the other. So anyway, but that's where we're starting. So what is in it, though? Because 8K represents almost all of the programmable space in the first computer I owned to do nothing, right? What on earth is going on here? So I'm going to use some of the tools of the trade to sort of poke through and work out what is in there, and I'm going to use Odr Jump. Does anyone use Odr Jump out there? Yeah, there's a whole, oh my gosh. Are you going to be telling me? There's more people out there that know what's going on than I am. And I'm going to say to Odr Jump, hey, can you disassemble that? Because presumably there's code in there, and that's what's taking up all the space. So the minus lowercase d in there is the disassemble. The capital C means do the horrible demangling, so I get to see C++ stuff. And the dash no show raw means I'm not interested in seeing all the bytecodes. I just want to have an idea about what the code is. And this is what we see. And this is, I have to slide around a bit. First of all, there's code that I didn't write. There's this _init function. Interesting. Here is a function called main, and it has zor eax ex ret. Now that's what I was expecting to see. 3 bytes, right? Zor eax ex is 2, and ret is 1. Brilliant. But what the heck is all the rest of this stuff? _start, pages and pages and pages and pages. But I didn't write this, but it's actually not that much. Right, let's work it out. The address of the last instruction is 40054C, and at the beginning is, oops, excuse me, 403B0, so that's 200 hex from beginning to end, which is 512 bytes. Okay, well, what the heck's the rest of it then? So let's just dump everything. Let's dump everything that's in this executable, and now we start to see what's going on here. There is a header with a load of stuff. There's some section headers with loads more things. There's program headers. There's strings. There's more sections. There's all this stuff. So what is going on here? And that's what we're going to talk about. We're going to say, what on earth does it take to make something executable and runnable? So you probably know that on Linux, the file format for the executables is called ELF. ELF is the executable and link format. And it comprises a header at the top which explains, hey, I'm an ELF file, and this is the kind of, these are where you can find extra data about me, what architecture I am, and that kind of stuff. It has a program header table which explains, to load me as a program, you need to do these operations. It has chunks of binary data which constitute sections. We'll talk about those in a second. And then at the end, there's a sort of section header table that explains where all those sections are, what their names are, what properties they have. It's not a great picture, by the way, but it was the easy one to steal from Wikipedia. So sections. What are sections? They're blocks of code or data in the executable, or maybe not even in the executable. We'll get to that. For example, the code itself is stored in a section with the name .text. Why it's called text is beyond me. But I don't know, for those of you who've been using Unix for a while, you've probably at some point tried to overwrite a program that's running, and you've seen that error, text file busy. And so in my mind, since as an undergraduate, I was like, what is this? Is it like some kind of tome that the processor is leafing through page by page, reading? This is the text from which it reads. But for some reason, code is text, fine. The read-only data is separated out. It's separated out because then it can be loaded somewhere and marked by the processor as read-only. Any attempt to write to it would cause a programmer fault. The data section contains data, and it's readable and writable. And then it's BSS, so there's a lot of strange things. We've already said that text is a strange name. BSS is even stranger. It's the block started by symbol. Now, I think somewhere along the line from the mainframe technology that this was developed on, the meaning behind that has been lost. But BSS now to everybody means zero initialized data. So if you've written anything that's at global scope or explicitly or otherwise set to 0, it gets put into this BSS section, which is going to be cleared for you. The cool thing about that is that doesn't have to be stored in your executable. There just has to be something in the executable that says, I need 16K's worth of zeros, please, over here. And that way we don't have to store all of that zero initialized data. I know it would compress really well, but why store it if you don't need to? So let's go on to a more interesting than an empty program. And in this one, we're going to do something which you should not do. That is, we're going to have a global object which has behavior that runs at construction time. I mean, don't have globals, if you can avoid them, obviously. Although there are definitely some globals out there. Now, who can think of a global that exists in C++ that's good? Oh, yes, thank you. Yes, std_cout is a global variable, right? So presumably it has a constructor and it has to do something quite interesting, right, during its construction. So we're going to sort of look at it from the point of view of our own objects, but again, don't do this. This is not best practice. I am not Jason Turner. So we've got a foo class. It counts the number of foos that are in existence, right? We've probably all done something like this before to sort of diagnose problems with leaking objects or stuff like that. And I'm going to use a static counter to count the number of foos that live. And then, C++ being what it is, I have to, say it up here and then say it again down here to define it. And then in the same file on the right-hand side, I've got it as a global object. Who would like to say what they think this program outputs? Undefined? Someone saying over there? Anyone? 1. Numfoo's equals 1? 0? All right. What does it print? Well, if we run it, and I'm going to run it with 0 here, just because the code later on that we're going to look at is going to be that much easier. Numfoo's equals 1. And it is my belief that this is well-defined behavior, because by not specifying numfoo's with a value, it is a global or statically initialized thingamajig, which gets put into that BSS section. I beg your pardon? Right, there's a discussion as well. Yeah, I don't have time, unfortunately, to go into that bit, but numfoo's is equal to 1. Okay, so somehow, before we get to that cout, numfoo's has become 1. Now, there are a number of ways that could have been achieved, right? The compiler could read through my code and go, hey, this must be 1. There's no reason why for it to ever be 0. I'm just going to write a 1 in there, and it's 1 forever. Okay. The compiler could be inserting code at the top of main that calls the constructor to global ahead of me to sort of ensure that it gets updated. But how would this... which one of those is happening, or is something else happening? I'd love to know, because that's a kind of weird, spooky thing that happens outside of the domain of the normal program. The way that I went around finding this out is to bust out the debugger. So it occurred to me while I was doing this that I didn't actually really understand this myself, and that I'd agreed to do a presentation on it. So what I thought would be more interesting than me reading up on it and then just regurgitating it is showing you how I discovered how this stuff worked. So I have inside this live directory that global example, and I'm going to run GDB on it. Oh, and I meant to do GDB-Q. So let me just list. There is my program. I've loaded it in, and what we can do is, I haven't even started executing the program yet, but I can ask GDB, hey, what is the value of foo num foos? Oh, num do's, num foos. There we go. It's 0. Okay, so clearly my first sort of hypothesis of somehow the compiler reasoned that I could never see the value other than 1 is not true. It's 0 when the program starts up. So let's put a breakpoint on main and run. Okay, so we're now on the line that's about to see out the number of foos, and I'm going to disassemble it. And for those who don't speak GDB or even assembly, that little equals thingamajig there is the next instruction we're about to run. And this is the beginning of the main function itself, and all that's happened before where I am right now is some stack manipulation. So there's nothing up my sleeve, there's no tricky instructions that are about to do anything other than that. What is the value of num foos here? Clearly, there's no code that's had a chance to look at the number of foos, so let's go foo num foos 1. Okay, so somewhere in between me loading the program and the first line of main being called, that foo got incremented. Now we could get clever and do some write breakpoints and all that kind of stuff, but it's much easier just to put a breakpoint on the constructor itself. So I'm going to put a breakpoint on the foo constructor, and I'm going to restart the whole thing. So run. Yes. Okay, so we're on the line that's incrementing num foos. Where did we come from? Backtrace. Okay, so that's my code, and then there's some funny looking things there that I didn't write. So that's enough of live GDBing. This is what the call stack looked like with nice colors, so we can sort of look through it. So there's code I wrote, foo : foo, and it's attributed to line 6 of global.cpp. Here are 2 functions I did not write. And in fact, if I had written, I would be wandering off into undefined behavior land because they have 2 underscores in them, and you can't put 2 underscores anywhere in the name. And I think the other rule is you can't use underscore, a leading underscore, and a capital letter afterwards. So these are symbols that I'm not allowed to write. But they've both been attributed to global.cpp, my file, at various points. So that's interesting. The next 2 are libc functions. Libc, not libc++ or anything to do with C++. This is the C runtime starting up. And ultimately, it was called from underscore start, no main at all. We're nowhere near main at the moment. So something else is going on before we get to main. Where on earth do those functions come from? Those funny underscore static initialization. Well, there's a website for some of this stuff. Let's go and have a quick look. Sorry. So we can go and find them over here on the right-hand side. Here's static initialization in destruction, and it is attributed like the thing says. You can't really see all that easily on there. The line 18 on the far left is showing that somehow this static initialization in destruction function was generated at the same point at the end of the file, or maybe the closing brace of main. It's actually the end of the file. We can't tell in this example. And then some code down here which is calling foo : foo, global foo. So this is the global constructor of foo, is in the middle of that function. And that is attributed to the actual definition of foo. So again, something seems to have happened when I defined a global variable and the compiler emitted some code somewhere into some magical function that it's writing for me. And then there's another, this is this other global sub I : num foos function, which just all it does is call static initialization in destruction. Okay. But who calls this function? Oh dear. Yes, no. I was going to say, how does it get to my function? That's the bad title for this slide. How does it get to this function? Well, at this point, I've been doing a lot of this stuff on my commute in and out of work, and so I have very spotty cell coverage. But at this point, in my sort of spelunking, I discovered that I had decent enough internet to Google for that libc function name, and I was able to find the libc source code, pull it down, and have a look. Oh, darn it, sorry. Forgot about that slide. So, if you've ever looked at the libc code, it is beautiful, it is wonderful, it is a testament to engineering skill, but it is not the most readable code in the world, mainly because it has to support pretty much every platform going and every architecture going and a lot of different compilers too. So you'll forgive me for having paraphrased this down to the very small bit of code that's going on. So this is that libc CSU init. It was one of the functions that had been called from that underscore start that ultimately called my function through those funny underscore named functions. And so, I don't know about anyone else here, I can't read function pointer syntax nakedly, so I have to type def it, or I should have done a using here, I suppose, but this is a C file, right? So what this is doing, for those like me who need to look at it every time, is defining a type called init underscore func, and that type is a function, a pointer to a function, I should say, that returns void, takes an int, and two char star stars. Int and two char stars, try saying that. Two char star stars, that's sort of strange. That sounds a little bit like the signature to main, right? Okay, so that's the init func. It then also defines two externally defined symbols, and they've called underscore underscore init array start and underscore underscore init array end. And they are defined as being arrays that live somewhere else, out in space somewhere. And then we subtract the end from the beginning. That tells us how many things are in this apparent array of things, and we call each in turn. And we pass in argc, argv, and envp. Who've forgotten that the envp could be put on the end of main? I had before I looked at this slide here. There's the third parameter you can use, yeah. Okay. But where do these init array start and init array end comes from? It's clear that something is going on where an array of function pointers to things I would like to run at startup has been constructed, but I'm compiling my one file at the moment, and presumably every file I compile that has a global would like to have its functions initialized as well, but how do I build an array of contiguous function pointers when I'm compiling a whole bunch of things separately? I mean, if you try and think about how to do that in C++, I don't know if you could, across multiple translation units, combine together something like statically. Jason's now starting to think as to see if you can come up with a solution. You can see. Well, there's a clue. If we go back to the example we looked at before, and I know probably this is all noise to you whenever you use Compiler Explorer, but these funny things at the top. If we take out the filter which turns off all of the assembly directives, then we get to see all of the other things that the assembler is told by the compiler. And if we scroll far enough, actually, let me just zoom down to it. Somewhere after all of the code has been emitted, and there is that funny function, the global initialization function, there's this section, sorry, overloading the word section here, there's this part of the code which has a dot section directive in it and a whole bunch of things. And so there's a clue there. Oops, sorry, forgot to close things. There we go. So it's this bit of code. And so what this is doing is it's a hint, or it's a directive to the assembler to say, you're currently assembling code and you're putting it into a bucket called the text bucket, right? We know that the text is where the executable stuff goes. Can you now switch over and start putting things into a different bucket? And that bucket I'm going to call init underscore array. Section is probably a better name than bucket because that's what they really are. Aligned to 8-byte boundaries, and then I want to put a quad word, an 8-byte pointer to you and me, that points to the function. That function that we defined, the one that has the initialization in it. And then the .text is shorthand for .section, go back to putting stuff into the text bucket. So we've kind of bifurcated the program at this point. We've got code that's going into one block, and we've just put something into another thing called a section. And we've given that section a .init array, which was not one of the ones I mentioned earlier when we were talking about .text and BSS and all that stuff. Interesting. Well, in order to work out a little bit more about what's going on, we're going to have to talk about the linker. What does a linker do? What do we think of when we think of the linker? Magic. That is a good answer, actually. I mean, for the longest time, the linker always just seemed like that annoying long step that couldn't really be parallelized at the end of my build, and that seemed to take up tons of I/O and all that. But No, it has a lot of work to do. And if you look into what the linker's doing behind the scenes, you get there's a deep, deep rabbit hole. So trivially, the linker collects together all of your object files that you gave it, resolves references between them. We know that in one file you may refer to something that was defined in another file, so there must be some way of tracking between those two. One thing I hadn't really thought about until I presented these, until I prepared this talk, was that it also is responsible for determining the layout of the executable, like where the bits go in the actual binary. Like, does main happen at the beginning of the block of code, or is it at the end, or anything like that? And you know, in conversations with people prior to this talk, it's also doing some like graph theoretical stuff where it's following dependency nodes of like, this symbol needs this thing, which means it needs that thing, which means it needs that thing, and stuff like that. And then it writes the metadata as well, which says, okay, I've finished with your program, here's the program header, here's all the bits, and this is where I put them. We've got a slightly more representative program now that's actually in two files so that we can see how this link process is going to come together. It's the hello world, and on the left-hand side, we've got the bit that does the printing, and on the right-hand side, we've got like a pluggable get message function, which we've written somewhere else. So main calls greet calls get message is defined in a different file. We compile them in the obvious way, link them, and it does what you'd imagine. No surprises there. What are those files that we generated, though? I kind of glossed over it. Normally, we just type make, or we take cmake, or we do whatever it is, and we know that somewhere there's an object file, and ultimately there's an executable, and the linker kind of brings them together. But what are those object files? Are they just like big assembly files or something? I don't know. Well, this is where you bring out the Unix tool file, which is like a great, I have no idea what this is, please tell me what it is tool. I don't know if anyone uses this regularly. It's just one of my favorite things to run. It's amazing what you'll discover, like, files are that you just find on your hard disk. And it turns out that, well, hello, no surprise, is the elf executable we were expecting it to be. But hello.o and message.o are also elf files. I guess the L in elf is linker file, so executable in link format, so not too surprising. And you know, we just saw that the assembler is able to put things into differently named buckets, and those are sections, and so why not use the same format that we store our sections in for our executable for our intermediate files too. That also means that we can run those tools that we were doing before, objdump and elf, and all those, elf, whatever, sorry, I've forgotten now. The other tools, which will appear slightly. So here we're going to dump the hello.o. So this is the one that has main in it, and it calls greet, which calls the get message, which is defined somewhere else. And we can see, here's the greet function, and we know that greet is calling get message, and then it's going to call operator chevron-y thing, the streaming operator, to stream that out to cout. And so the first call is going to be to get message, but it's apparently a call to greet, which is weird because this is greet. Is this like some crazy recursion thing going on? But more interesting, if we look at what address it's calling the next instruction. Why on earth would you call the next instruction? Well, obviously, we don't know where get message is yet. It's somewhere else. We have yet to define it, right? When the compiler was emitting this code, it said, I know that somewhere exists get message, but I don't know where. So it leaves it blank. And you can see that. So in this instance, I have shown the opcodes. So E8 is the opcode for call, and then there's an offset here. This is an offset to where I would like you to call to. And because the compiler and the assembler don't know, they've put zeros there, and then said, okay, linker, you figure this out, and you put it here afterwards. And it just so happens that this offset is relative to the next instruction, which is why 0000 actually looks like a call to the next instruction. And it's actually relative, yeah, we'll go into that in a second. So there's a whole bunch of these. And interesting as well, even though main here, in the same file, is calling greet in the same file, it's also just calling itself. And it's letting the linker determine where that is going to end up. You'd think that because they're in the same file, it could actually just call between them directly. Like, I know where I put this, so I'm going to call it. But it doesn't. It chooses not to. There's a subtlety to this because main is actually tagged to be in a slightly different section name from all of the other things in the main. It's in like a .text.init section. And that prohibits the compiler from doing some optimizations that it would otherwise do unless you're on like the highest settings. And interestingly, as we'll see in a second, the sections are kind of like the primitive unit that the linker has to work with. It doesn't know what's inside each of those sections, so it has to move them around chunk by chunk. And so by putting things into more sections, you're giving the linker more flexibility in where it puts stuff. But obviously, then it needs to patch the code to refer to, sorry, I'm going to go to the next slide where I actually explain relocation. So we're going to talk about patching. So those 000s that were in the middle of the opcode need to be turned into something by the linker, but we need to tell the linker what it is we would like to put there. So here is me dumping it with relocation information. So I've used Odr Jump again, and I've used a different flag to say I'd like to show the contents of the relocation section. So there's actually a separately named section inside the object file that describes all of the things that need to be done in order to link my executable. As it happens, Odr Jump is good enough, nice enough to interleave these, even though they're in separate blocks of the file. So here we can see that the push and the call are, are defined here. And then there's this funny thing at apparently address 5, which says, hey, linker, can you go and find get message? Wherever get message is defined, go and find that address. Then subtract 4 from it. And then please, can you poke it in using this particular kind of poke, the RX8664 PLT32, at address 5. This is the 5 here. So address 5, of course, is, well, there's 4, so this one's 5. So this is it saying, write 32 bits worth of data that refer to get message and put them here in the middle of this instruction. And similarly for the other calls down here. And in fact, we didn't notice, or I didn't point out, that here is a reference to the cout global object, which also needs to be patched up in a particular way. But you notice there are different types of patches here. This is a PLT32, which is a procedural linkage table, which we'll get to if we have time at the end. And this one here is a GOT, global object table, PC relative thing. So there's some different things going on here. So the takeaways really here is that the linker needs to be told how to find the symbols, which symbols to find, and then when it's found them, where to put that information inside the binary blobs that represent the assembled code. There are different types of relocations. We saw 2 of them just there. It's worth noting that those types are dependent on the kind of instruction that it's patching and the architecture that the linker is working on. So if patching an ARM instruction is very different from patching an x86 instruction. And in fact, there may be some things like where constants that can't be expressed in one instruction in ARM have to be like bust into 2 parts and like ordered together. And so there are different like link types that will push, different relocation types that push like the top 16 bits into this bit and the bottom 16 bits over here, things like that. They're also used within the same object file. We saw that between main and greet. So if the compiler has decided to elect to put things into different sections, it can still refer to things within the same translation unit, the same object file, using and let the linker do the hard work of working out how to put things together. So let's talk about the symbols. So I just sort of said, hey, go find get message. But where is this get message bit coming from? How do we know where get message is? Well, there's another section in the file that says, this is where I'm defining all of the symbols that I need, or I provide. So if we use Odr Jump again and say, what symbols do you provide? Hello.o. If you remember, again, hello.o is the main function. We can see that there is a whole bunch of symbols being brought in. This left-hand column here, L means it's local, whereas G means it's global. So these are local things that are less interesting to us. Although you'll notice that the static initialization and destruction and the global sub-I magic functions are listed in there. Although this isn't our global example. Our greet function is here, and our main function is here. This F means it's defined in this file. And you can see there's a whole bunch of undefined symbols which are like, hey, I need these somehow. Someone else has to provide these for me. So obviously, if we were to dump message.o, which just contains that getMessage function, we'll see that, yes, it defines getMessage as a global symbol. So then, the linker, sort of, reads all of the inputs. You give it all the obj files. It identifies all of the symbols that each of those object file provides. It works out then which symbols provide which relocations, and it lays out the file in some yet to be determined way. But we start with maybe with main. We put main down, and then we say, okay, main. Oh, we need to find this thing. Okay, go find it. Put it here. Now patch the references into it, and so on. So we can see how that could work. Okay. Let's just go through it in a sort of pictorial way. So message.o here has 2 sections. The blue are sections. We've got get message, and of course, there's actually some read-only data in there. The actual string hello world is a string constant, and the bytes for that need to go somewhere. And then hello.o has a greet function and main. And the linker effectively is going to do pretty much as I described, collect together those things, output them in some kind of order, and then we're going to have a .text on the way out and a .ro data and some program headers that say, hey, this is where to find the things you need, Mr. Operating System, or whatever process loads and runs it. And you'll notice here that the greet and main are defined in two different sections, but they've ended up in the same section in hello. So you might just think to yourself, okay, so the linker has a hard-coded set of rules that say, collect together everything called this and emit them over here. All the sections named this, pick them up, put them over here, and then link the things between them, do all the relocations. But of course, that's not the case, because linkers can be used for more than just boring executables. The Linux kernel, for example, is linked with a linker, and so it doesn't have a regular layout like you might imagine. For those of you that have worked with embedded systems, you probably know that there are some sort of magical addresses that you like. I just need my code to start at address 1234 because that's where the CPU is going to start jumping to once I power it on. And so I need to be able to lay out things in a much more structured way. And the way that you do that is through a linker script. And so here I'm just running GCC and saying don't do anything, but we run the linker with verbose. And, oh, for some reason, oh, blast, sorry. This is the problem with these things. Linker, yeah. Okay, so we're going to quickly just scrim through this. So the linker at the top here, if we dump it out in verbose mode, it prints out the linker script, which is effectively a programming language in which you tell the linker what you would like it to do. You set the output format and the architecture. There is an entry. Now, this is a hint to the linker, it's a directive, to the linker to say, when you write out that program header table that tells the operating system what to do, this symbol is where you should say, address the start here. So there'll be a field somewhere in the header that says, this is the first instruction of my program, and it should be called _start. So that's setting up the metadata. And then the most interesting part here is the sections table. So this sections table is going to explain how to take all of the sections that are coming in from the input and put them into the output. And so, for example, we'll just pick one at random at the top here, .interp. Whatever .interp is, in the output, what we're going to do is we're going to take every every object file, and find its interp section, and just basically concatenate them together. So this is a way of picking up all the interp sections from all the files, collecting them together, and then putting them in a section in the output called interp. And you can see there's an awful lot of this. It's pretty complicated, but in the middle of it all, interestingly, we see a reference back to init array. You remember the global thing we were looking at right at the beginning? This is interesting. So here it is syntax highlighted. Now we can actually see how that init array was populated. So what it's saying is that in the output, I want you to create a section called .init array. We're going to ignore this top line for a second. We're just going to look at this keep. Inside of that init array, we're going to pick up everything called .init array from all of the source files. So here, every global we would have defined would have made its own .init array section, and then this thing says, pick them all up and just plonk them all together, one after another, inside a section called .init array. Cool. Okay, so now we actually get to see how those apparently disparate pointers that were defined in different files get put together into a single contiguous array. I mean, it gets very complicated with the C runtime here, also using the same mechanism. Interestingly, up here, you'll see that there's a set of things, the .init array dot something, which can be sorted by the linker by some level of priority. Now, I've observed that the C++ system by default does not use this technique, but if you delve deep inside the implementations of like std_cout and things like that, it's possible that they're using some extra tagging and sort of magic annotations to say, no, please sort me to the front of the initialization list so that cout is like ready early. I know that libc doesn't do this. We were talking about this earlier, but it's possible that other implementations do. And certainly, if you look at the C documentation of, say, GCC, there's an attribute you can give to functions which says put it into this section with this priority and this sort key, effectively. The other thing that's defined here is that these provide hidden. So it turns out that the linker script can make up new symbols as it's running, which is pretty cool, right? So what this is saying is that please create a new symbol called __init array start and assign it the value of dot. And dot is a magic thing that says where I am currently outputting to. So this is the address of where I am right now in my link process. So we've effectively put a marker down called init array start. Then we've gathered together all of the, first of all the things that have a priority sorted by their priority, and then the everything else bucket that all of your global constructors will have been put into. And then at the end there, in that last bit, we provide a .init array end. So we now have bounded everything that we need to run with a start and end. That's pretty cool, right? And it's also, you'll notice, why you should never use global variables, because you don't get to control which order they get plonked down in. And I've had all sorts of horrible bugs where we've inadvertently relied upon that, and then it's been like the inode order on the system that has actually ultimately decided which way round things get initialized. And just don't get there. Don't use globals. This is not a best practices talk. Oh, I forgot that I highlighted them. So now we know how that global process works. So just to recap, the compiler makes a static initialization function in every translation unit, which calls out to all the constructors for the objects that are global to that particular translation unit. It puts a pointer to this function into a section called init array. The linker then gathers together all of those init arrays and puts them one after another, and the script kind of bookends it by putting a tagged symbol name at the beginning and the end of that. And then finally, the C runtime walks through that init array and calls each in turn. So now we know how global constructors work. Ooh. Things that are interesting about this is that those linker scripts aren't just for the compiler. There are some situations in which you want to write linker scripts yourself. Again, if you're an embedded system, or if you are writing a kernel or something like that, you might need to control very, very carefully the output of these, the order or the addresses that things get assembled to. It's also interesting, I noticed while I was looking at this, that some dynamic objects, some DSOs that you're linking against or referring to, aren't actually DSOs, they are linker scripts. And the linker, when it sees something to link against, will look at it, and if it looks like a text file, it will interpret it as a linker script and will follow the instructions in that. So you can have some link time behavior defined in those, which can be used for versioning tricks. The linker as well, like I said, it has a graph theory thing in it where it can actually work out which sections are unused, and then it can throw them away. I didn't show you, but back in here, the keep part, so the keep that it's saying here, is a hint to say, even if you think this isn't being used by anyone else, keep it, because of course there's no way it can tell that these things are actually being used by the C runtime. So let me just go back to here. So yeah, you can tell the linker to garbage collect sections that are unused. It's not on by default, and I'm not quite sure why. One thing to note here is that the section, apart from the relocations that poke into it and change the instructions, the sections are essentially opaque binary blobs to the linker, which means that it can't discard an unused function inside a section because it doesn't know that a function exists inside of it. It's only if a single object file has a section for which there are no references pointing into that the linker can discard it. So if you've ever wondered why your executables maybe contain functions for which you think, well, why has this not been thrown away? It's because the linker couldn't throw away the section that function was defined in. There are flags to the compilers to say, well, if I put every function in its own uniquely named section and every block of data in its own uniquely named section, I'm giving the linker the ability to have a much more fine-grained ability to throw things away, and you can turn those on. But it starts to prevent optimizations between functions that you would otherwise be able to do. So these are very advised things. If you really think you can squeeze out a bit of size, it's worth testing these both before and afterwards and being totally sure that they're the right thing for you. But they exist, and it's interesting to know. All right, how are we doing? Good. Excuse me. So now we get to the thing that I was most interested in working out, dynamic linking. So the 7K executable we saw earlier doesn't have the C, the whole of the C runtime in it. I think that's clear, right? We saw bits of it, that libc stuff, but it's not like I saw loads of bits of code that referred to the operator overload of OStream and all that kind of stuff. And that's because the code isn't in my binary, it's somewhere else. And in fact, this is kind of the level at which we're talking. If I do a dynamic link of my hello executable, it's just over 8K. So the 7K one was for the empty case, if you remember. This is just for the hello world one. But if I were to statically link it, it comes in at 2.5 meg, which is quite big, right? I mean, there's a lot of stuff going on in there. There's a lot of C++ runtime stuff in there, and probably for all the reasons I was just describing, the linker can't see that I'm not using bits of it and throw them away, so I'm stuck with it all. So dynamic linking is going to help me here. So let's just rephrase our hello world and see what it looks like if we use a dynamic link aspect to it. Now, obviously, the C runtime is far too complicated for me to delve into right now, so I'm going to split my hello program into the main and the other bit, which returned the get message, and I'm going to make the get message a DLL. Sorry, for all those who are Linux people, I'm sorry. DLL is what I'm going to say. DSO, I know, is the right term for it, but I think you know what I mean. So this is just the relatively straightforward of linking that as shared, and then saying, please find get message in the libhello.so, and it works. And by works, I mean it doesn't work because DLLs are a pain in the backside. That's a good. The question was, why didn't I provide fpic? And it's because I forgot to put them on the slides. Thank you very much. Yes. In order for this to have worked, the code must have been compiled with position independence, which means that it can be moved around a bit. There's more latitude in where the linker can lay things out. So I did do that. I just haven't put it on these slides. Thank you for the comment. Also, I didn't put in here anything to do with like the R-path catastrophe that you have to do in order to make it actually work meaningfully all the time, but that's a whole other talk. So let's have a look at what happened. We linked the hello executable, and I'm now saying, well, I did readelf minus help, and I looked through it, and I went, oh, these things sound interesting. What is the dynamic section, and what are the program headers here? So the program headers include this thing called interp, which you'll remember we actually saw when we looked earlier at like how the sections are being laid out. And there's this interesting annotation here, requesting program interpreter, blah, 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 blah. Interesting, okay, we'll note that, we'll come back to it. Some mappings, and then here, there's a section called the dynamic section, and here is a load of metadata, and you can see that libhello.so is mentioned. So this is where somehow I'm communicating to the operating system that I need to find libhello.so and load it in before I can be run. And then there's the dreaded R-path. We won't talk about that. So let's do some more archaeology. What happens? So I have another example here. And we have, there's the hello one, okay, live hello. So it's just list that. There's our function again. I'm going to put a breakpoint on greet, and I'm going to run it. And then, so we're about to call get message, and we know that get message is defined off in the DLL. And if I disassemble, we're about to call underscore z10 get message v at plt. There's that plt word that we saw earlier. If you remember, that was one of the sort of mystical sets of letters that were inside the R relocation. And I just sort of glossed over it saying it stands for the procedure linkage table. Well, this is how the dynamism bit comes in. So that's not calling directly to get message because we haven't worked out where get message is yet. Linux by default is lazy about looking symbols up, and we'll say why in a second. So this call goes to a thunk or a trampoline or any number of those funny things. So I'm going to actually break on 40060. And actually, no, I'm going to do step I. Okay. Okay, so here I am now. I'm actually in that call. I just stepped over to it calling, and oh, that's interesting. I stepped too far. Sorry, let me do that again. Live demos. I'm going to just disassemble it directly. 4006BO. Oh, this worked before. I'm sorry. Ha! Oh, that's meant to be break on that. Hooray. Continue. Disassemble. Are you going to work now? Yay! Okay, phew. I can use a debugger, honest. All right, so this is the function, this z10 get message v at plt. And it doesn't look like my get message because I didn't write it. In fact, the PLT is a section that is generated by the linker, and every relocation to a function which is defined in a DLL, in a DSO, is given an entry, and all of the calls to those functions that are defined elsewhere come through the PLT entry instead. And it's a very weird looking thing, right? We've got a jump here, and then after it there's a push queue and another jump. That's really weird. And this jump, this syntax is an indirect jump. It's saying, hey, look up some other piece of memory, get an address out of it, and then jump to wherever that address told me where to go. Right, well, I'm not going to debug through that because we haven't got time, but here's what I did earlier. So this is what it looks like. So the reference to the memory address of where we're going is that 601018 that's at the bottom there. And at the moment, it's a value of quad 4006b6. What do we notice about that address? Where are we going to jump to? We're going to jump to the next instruction. This is a really, 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 really complicated way of going to the next instruction. Weird, right? I mean, we saw the call to the next instruction, and we kind of, well, that's odd, but then we found it. But this is absurd. We're calling a function, and we jump off somewhere, which comes back to the next instruction, which then pushes and goes somewhere else. And now, if we were to follow this through, we'd see that would actually happen one more time for very complicated reasons. But ultimately, what happens is that 4006A0 jump at the end goes off into the dynamic loading subsystem, which looks up what get message should point to, and then ultimately goes to that address. Okay, right, so presumably that's an expensive process. You know, I've got to look through all the symbol tables of all the DLLs that are currently loaded. Maybe I even have to load them off disk if they aren't already loaded into memory. And then I jump to it. That's a really expensive thing. We would not tolerate it if all of our calls had to go through something as expensive as this, right? So this ultimately resolves symbol 0. That's what that push Q is, by the way. It's pushing the ordinal in the symbol table that it's looking up. And it has to use push because every other register has something important to the function you're supposed to be calling, right? So it's just kind of having to use the stack as a back channel or a front channel, I don't know. The cool thing is that once it's done that resolution, once it's worked out where get message really is, it writes it back into that address at 601018. And so the next time get message is called, that first jump goes directly to get message. So that's pretty cool, right? We actually kind of patch a code as we go. Every time we call a function that's in a DLL, the first time we call it, there's this expensive process where the lookup happens, and then after that, it's free, cheap, I should say. It's not free. An indirect call is a little bit more expensive. The branch predictor will pick that up, but you should stay and watch Chandler's talk as to why that is probably going to not be forever. Okay, so why does it do it lazily? Why does it not just look these things up at the beginning? You'd think that like you load your executable and it would just do the resolution there and then. It's got the set of symbols, it's going to just go through them all and it should find out where they go. Well, there's a whole bunch of reasons why. I mean, the first thing is that the C runtime has a ton of functions and hardly any of them are called by anyone. I mean, if you imagine like every time you type ls to list a directory on Unix, you're firing up a new executable, running it, and coming back out again. And so if you were to do the work of looking up all of the functions that it didn't call, you would slow down the startup time. So it's like a lazy optimization about how starting up your application should be fast. And then you only pay for the functions you use. Hey, see? Only pay for what you use. This is not always what you want, though. For example, if you work in the finance industry, and I mean, you shouldn't be using dynamic libraries anyway, but if you happen to be, and you wanted to make sure that every time you called a function, even if it was the first time, it's quick, you need to ensure that that happens ahead of time. And you can force it to happen ahead of time. So you can set an environment variable, ld bind now, and if it's set, then that's a hint to the system that it should just straight away apply all of the relocations and fill in that PLT with the actual addresses rather than the one that goes to the resolver. You can also specify it as a flag in the linker, which marks a bit that says, please do this. And incidentally, what is the thing that is doing this, right? I sort of waved my hands and said, oh, the dynamic linking system, and I even deliberately said, oh, and the kernel or whatever. It's not the kernel. The interesting thing here is that that interpreter that I glossed over before is actually what is doing that work. So the kernel's job is to load in the program, read through the program header, which loads in just a few blocks of your program, and then if there's no interpreter set, it jumps to the underscore entry address. But if there's an interpreter set, it also loads in the interpreter and puts it over here, and then jumps to the interpreter, giving it the underscore entry address as like a parameter. This means that now the kernel can go away and say, I've done all of the things I needed to do to set up a process to start executing your code, and now I'm out of kernel mode, and I don't need to do touching the kernel to change this. I've given it over to user mode entirely, and as an executable, that interpreter, the user lib64 LD thingamajig, which is now responsible for starting the whole DLL process. And it will ensure that the PLTs are loaded. It will follow the dynamic section and make sure that each of the SOs that you need can be found and are mapped. And then it will provide effectively the service to which they are jumping. That's why that first, I pointed out in the slide, this like the fourth instruction jumped to something which then did the same dynamic lookup again. It's because the interpreter itself is effectively mapping. Yeah. Anyway, magic happens. Magic happens. I just realized haven't thought this through, and I'm thinking it through as I'm here on stage. I'm thinking this is not a good time to be thinking up new content. Anyway, so that's what happens. The interpreter is responsible for doing all of the clever machinations and reinterpreting the sections that say what dynamic stuff needs to happen. And if you've ever had problems with, for example, your R path, and you've wondered, hey, what is happening inside this dynamic system? It's really complicated. I run my executable, and I've got like a stale result. I'm sure I changed my code. We've all done this, right? I edited my code, and the bug's still there. What did I do wrong? And I mean, normally you've either edited it on the wrong computer, or a wrong copy of the code, or you forgot to make, or your make file failed, or maybe you just recompiled a DLL, and it's in the wrong place. And so you're not actually loading the DLLs you think you're loading, those kinds of things. Now, to debug that, you can run LDD on your executable, which says, hey, this is what I'm going to resolve these things to. Excuse me. Or you can set the environment variable LDDebug, which the interpreter then uses to sort of print out to Studere loads and loads and loads of things that it's doing. And it's fascinating to turn it on and just look at what the heck is going on behind the scenes. You can do LDDebug equals help, and then you get help. Otherwise, I typically use LDDebug equals all, and then trawl through it all to work out what's going on. And for example, you can see that lazy loading and symbol resolution thing. I actually did it on LS, and you could like pause LS in the debugger, and then you could continue it and step through it, and you'd see all these functions it's calling being like resolved and being output out. It's quite fun. This leads us to another thing you can do, which is, because it's lazily done, I can interpose myself into the whole proceedings and say, I'd like you to do something different, actually. You can set LD preload, the environment variable LD preload, and as long as it resolves to itself a shared object, your shared object that you've specified will be loaded ahead of time, and its symbols will be injected right at the front of the symbol resolution process, which means that you can steal any dynamically referred to symbol that's in an executable, right? You don't have the source code to the executable anymore. Maybe you lost it. Maybe you never had it. But you'd be really interested in instrumenting calls to, I don't know, open or write, things like that. Well, you write your own open and write. You compile them into a dynamic library, and you LD preload them. And then you run your executable. So you do LD preload equals my so / executable I'd like to look at. And that allows you to actually interpose and steal those things away from a pre-built executable, which is kind of cool, right? I mean, for example, if you run a website which allows users to arbitrarily run compilers and do anything, you probably want to make sure that they're not opening files that they shouldn't be opening, not hash including etc. shadow or something like that. So you could do this, right, on open and say, if the file matches some blacklist, then return eno_perm, right? Which is what Compiler Explorer does. Another thing that a friend of mine told me, which is hilarious, is that they had like a mathematical analysis tool system, and he suspected that their mathematicians that provided the service weren't really up to much programming-wise, and that although it was taking many hours to run simulations that they were getting, that actually probably the problem was that various transcendental math functions were being called over and over and over again with the same numbers. So he instrumented some of the signs, hyperbolic sign functions and things like that, and replaced them with something which just kept a histogram of what input values they had. And it turned out that, yes, 97% were calling like sign with the same thing over and over and over and over again. So he was able to go into them and say, well, A, fix your code, but B, I can fix it here for you. I can put some rudimentary caching into your F sign, and now I make your program run faster. So that's quite cool. It's also used by some networking systems that replace like the traditional networking layers inside the operating system, so that you can like do direct access to cards that provide kernel bypass. There's a load of cool things you can do with this. If you're interested in that, talk to me afterwards. Okay, I have very little time left. I really wanted to get to some of the other cool things that are much more C++-y. So weak references. You know that if you define foo, the function foo, in two places, and then try and link, you're going to get multiple definitions, right? and that's, mea culpa, I shouldn't have defined it in 2 places. But when I make an inline function, I'm kind of defining a function in 2 places, and sometimes that function is genuinely inlined, like in terms of like the optimization process, it's inlined, but oftentimes it isn't, which means that if I've used, my getFoo function, my inline getFoo function in translation unit A and in translation unit B, there's 2 copies of it. Why does that not cause an error? And the answer is it gets marked as a weak symbol, which is another tag that I didn't have time to show. And the weak symbol, the linker says, it's OK to have as many of these as you like, but you get to pick whichever one you like as the implementation of getFoo, which is great, provided they are all actually the same. And again, the linker has no idea. These are just bags of bits as far as it's concerned. So it can't look at the implementation of getFoo or whatever and say, oh, this is the same across all translation units. That's fine. So this is where ODR violations show up. If you've kind of got 2 implementations that are marked inline of the same function, defined to be slightly different in 2 areas, disparate areas of your code base, and then the only time that they actually come together is in the linker, you're in for a shock. The last thing I would have loved to have talked about would be link time optimization, where the linker actually starts collaborating a lot more closely with the compiler, and there's a sort of 2-way relationship. The compiler generates an intermediate form rather than just assembly that is a bag of bits. It has a much more rich intermediate representation that's then passed to the linker, and then during the process by which the linker decides which things are visible or can be reached, it calls back to the compiler and says, hey, I need the code for this now. And the compiler gets to see the whole world as the linker has laid it out. And some amazing optimizations can happen there, and actually some ODI violation checking can happen there that you would otherwise not be able to catch, which is great. So that's the way I've encountered some subtle ODR problems before, is by just turning on FLTO. So I recommend you all doing that anyway. There's a whole bunch of stuff. So Ian Lance Taylor is responsible for writing the gold linker, which is the one I've been using most. It's pretty amazing how fast and how much sophistication goes into it, because linking is something you prefer not to have to do, just like compiling, right? So, and it's the only step that's inevitable in your whole build process unless nothing's changed at all. So making the linker fast is a super important thing. For the link time optimization, Honza's blog has got a whole bunch of stuff about how that works behind the scenes. I guess that's it. So I'm sure you have questions. I'd just like to point out that Jason Turner, myself, and Charlie Bay will probably be getting together sometime next year and doing a training event, so you're welcome to ask us about that. But I invite your questions. I actually have 2 minutes left. Thank you.
So,
hello.
During the linking process, or during the layout process, when it's I guess my question is really about the resolution. You said the kernel has some role it plays by laying everything out. It's starting the process, it lays out parts of memory, and then it turns everything over to the interpreter script. And does it lay out every sort of dynamical object that is there, or does it kind of go, okay, I'm going to lay out some of them, and the interpreter can go back and go, hey, I need that thing.
Right.
Can you do that for me, kernel?
It's more like the latter. As I understand it, like the program headers have a few slabs that I say, load in executable text and put it at address, this offset of my file, put it at this address of memory, put read-only things over here, put the other bits over here, and then that's when it will jump to the interpreter, and all the DLL stuff then will happen in the interpreter, where it will read a specially named section that's tagged as being, this is the name of all the things I need, and that will continue on from there. It will mmap those in and mark them in the appropriate way, and then do the link resolution. So more like the latter. Cool, thank you. Over this side.
Hey, could you just clarify, at some point you said you should never actually use dynamically linked libraries?
Aha, right. Yes, so dynamic linked libraries, I say, that if you're writing highly performant code, you should avoid dynamic linked libraries. They're a barrier to optimization across units. Like, there's essentially the compiler can't see across them, even with all the clever, fancy link time optimization things that I'm starting personally to rely upon. And there's this resolution cost. Even if you do turn on the LD bind now, there's still a jump through the PLT to get to your function. So it's a little bit of a bump in the way. That's really what I'm saying there.
Okay. So if you statically link, you never get the PLT.
Correct. If you statically link, then the linker will just write into the instruction, jump to the actual location, because I know where it is.
Thank you.
Thank you. Over here.
In Windows, in portal executable format, there is a problem that every executable has an address that they want to be loaded at. And if it doesn't happen, there is basically similar process but happening at runtime. Like there should be like a relocation happening. Is it also something that happens in ELF Linux world?
So I'm not actually sure about that. I know that there are some preferred addresses that are marked inside the program header table itself. I don't know if they are required or not, and I'm not sure if there's a problem. Because I think specifically with DLLs in the PE format, this is a DLL that would like to be at like 4 million in RAM, and that's where everything's expecting it to be. Is that what you're?
Funny enough, like in Windows world, if your project is built of many DLLs, there is even an optimization technique that allows you to come up with some algorithm how you assign those addresses, like based on alphabet or something.
I see. So I don't think that's happening anymore, and mainly because of address space layout randomization, which means that every symbol wants to be shoved into some random place just to try and make it harder for the bad guys to get in. So I'm pretty sure everything now tries to be put into, like, make it as easy as possible to map it anywhere.
I see. Thanks.
Thank you. Oh, another one over here?
Excellent talk, thank you. Following on that question, how different will be all this in Windows?
Yes, good question. I think at the beginning I put my massive disclaimer that it's been about 20 years since I've touched Windows. So I think I will defer and say there are probably experts you can find here. If there's anyone who considers themselves an expert, and I'm not an expert at any of this, as you saw from me just like discovering this process kind of by myself, then I invite you to kind of raise your hand and speak to my friend here. James McNellis, yes, if we can find him, then yeah, he's a good person to find. Thank you. Sorry I can't be more help. Another question there behind you.
Could you explain what's the difference between a fix-up and a relocation?
No. No, I don't know actually. Is there anybody who could, in the audience, who would know the difference? I would assume that they're synonyms, but these things are subtle.
Like the compiler emits a fix-up, which the linker then emits the relocation or something like that?
I'm not sure how you're using the word fix-up here, but I do know all about ELF and stuff, because...
Right, well, if I defer to the right-hand side of the room in this instance. So the short answer is I don't know there. Oh, there's someone else having a conversation. But you've got a comment or question, or you can help me out here?
I was just going to try and answer the question.
Oh, I see, thank you.
I don't understand the question. So.
Right. I mean, there's a ton of interesting terminology like trampolines and thunks and other things that get used in this.
Yeah, in ARM, the linker will emit sort of trampolines to deal with out-of-range branches, because on ARM, there's a certain distance that a call instruction can go to.
Yep.
So the linker will see that, oh, I'm trying to go too far, and then it'll emit a blob of code between sections that it can, and then jump to that, which will then do a far jump to the target location-y thing.
Often wondered how that happened. That's clever. So I don't know if people got that, but like, there's the encoding and format of ARM instructions is such that the branch, everything's a 32-bit instruction in ARM if you're not in thumb mode, and so there's only a small amount of space in the instruction encoding to put the address of where you'd like to branch to, which means you've got like a plus or minus some amount.
I think it's 2 megabytes or something.
2 megabytes, right, which when I was doing ARM, 2 megabytes was more memory than I had in my computer, so that was great. But nowadays, obviously, 2 megabytes doesn't get you very far. So the linker has to know when the destination of a branch is too far for it to reach, and then it has to put a function whose only job it is to be like an intermediate post along the way to get to the final destination. Cool, thank you, I learned something. There's some heated debates over there. Have you got any other comments or thoughts there? Or?
No, it's fine. It was a good talk. Thank you.
Thank you very much. Thank you. I'm Ian Oe.